In this section, we're going to discuss lifting and sequential lifting, and we're going to keep as our running example cover inequalities for the knapsack set. We start by stating proposition 7.1, and I'm going to leave the proof as an exercise for you. In particular, this proposition tells us that among the cover inequalities, the minimal cover inequalities are the strongest one. So let's read through this proposition. Let capital C be a cover for our knapsack set K. Then the cover inequality associated with capital C is facet defining for this set PC if and only if C is a minimal cover. So what is this set PC? It is the convex hull of K intersected with xj equal to 0 for every j not in the cover. At this point, this set PC seems a little bit technical. So this is a very interesting proposition. However, what about facet defining inequalities for conv K instead? And this is exactly the question that brings us, in a sense, in the direction of lifting. So let's pick a minimal cover C, and the question is, can we compute coefficients alpha j for all the variables j which are not in the cover, so that the inequality obtained from the original minimal cover inequality, which is the one in green here, by adding the sum of the alpha jxj for all the j in n minus c on the left hand becomes facet defining for the convex hull of K. We will see that the answer to this question is yes, but in order to get there, I want to do things more generally and not just for knapsack sets and minimal covers. So let's look at a more general 0-1 linear set that we denote by capital S. Then pick a valid inequality where the only variables that appear correspond to a subset capital C of all the variables n. And let's assume that this inequality is valid for the convex hull of S intersected xj equal to 0 for every j that is not in C. Then we define a lifting of this green inequality, and it's defined as a valid inequality for the convex hull of S of the form that we have here. So essentially it is exactly the green inequality, but where on the left hand we are adding the sum of the alpha jxj for every j not in C. So let's see a couple of pictures that hopefully will clarify a little bit this concept. So here we just have a two-dimensional example. This triangle is our set conv S, and in green we have our original inequality. Now we have that the index 1 is in capital C. In fact, this inequality is x1 less than or equal to 1. So the only variable that appears is exactly the variable 1, which is in capital C. Therefore, the index 2 instead is in n minus c. Furthermore, this green inequality satisfies our assumption because it is valid for conv S intersected x2 equal to 0. And in fact, this inequality is valid for the segment here between the origin and the point 1, 0. So at this point, let's see some liftings of this inequality. One lifting that we can obtain is simply obtained by selecting alpha 2 equal to 0. In such a way, the new inequality is exactly equal to the old one. So we obtain exactly the same inequality. So it is of this form. Furthermore, it's valid for conv S, so it's valid for the whole triangle. So it's a lifting of the original inequality. Let's see another example, maybe a little bit less trivial. What about this blue inequality? In this case, the coefficient alpha 2 is definitely non-zero. And if the original inequality is x1 less than or equal to 1, this will be x1 plus 1/2 x2 less than or equal to 1. Also, this is a lifting of the original inequality. In fact, it's definitely of this form, and it's still valid for the triangle. One important thing to notice is that the intersection of this lifting, this blue lifting, with the hyperplane x2 equal to 0 coincides with the original inequality. And that's obvious because if you set to 0 all the blue variables, you obtain exactly the old inequalities. So all the liftings must coincide on the hyperplane where we started from. And this makes us immediately understand that in order to obtain the strongest lifting of our original green inequality, we need to essentially maximize alpha 2 in this case. So this is the strongest lifting that you can obtain. This is the inequality x1 plus x2 less than or equal to 1, and it is a lifting of x1 less than or equal to 1 because it's of this form and it's still valid for the triangle. Let's now look at an example that is a little bit different. So everything I'm changing is the triangle is now the convex hull of the origin, the point 1, 1, and the point 0, 1. At this point, we still keep 1 in C and 2 in n minus C. Therefore, the green inequality could be, for example, x1 less than or equal to 0. In fact, it is valid for the triangle intersected x2 equal to 0, which is just this point. So this is a bit less intuitive than before, but highlights the fact that the inequality we start from is not necessarily valid for convex, but is just valid for a face of convex. In fact, in this case, the lifting obtained with alpha 2 equal to 0 is again the same inequality and is not a lifting of the original green inequality. That's because it's not valid for the triangle. However, this inequality here in blue is instead a lifting of the original green inequality because it's valid for the triangle, and you can check it is of this form. And also here, in order to obtain the best possible inequality, we need to maximize the coefficient alpha 2. And if we do so, we obtain this blue inequality here. We can already understand from these pictures an assumption that will be fundamental in our subsequent lifting theorem. In fact, in order to obtain a lifting, even in this picture, we need to have at least one point in S intersected x2 equal to 1. Because think about it, if we didn't have any, let's say in this case our polytope would have been only the origin, then by maximizing alpha j we can tilt this inequality all the way until it's exactly x2 less than or equal to 0 essentially. And at this point this is no longer a lifting of the original inequality. So essentially it makes no sense to lift in such a case. So now let's state and prove our main lifting result. So we have a set S in 0, 1 to the n that satisfies this technical assumption that we just talked about. So S contains at least a point with xn equal to 1. So in this proposition, we have an inequality whose left hand depends only on the first n minus 1 variables, and it is assumed to be valid for all the points in S with xn equal to 0. Then we want to find this lifting coefficient alpha n, and we also want to find the best one. So we define alpha n to be beta, so the original right hand of the inequality, minus the max of the original left hand over all points in S with xn equal to 1. And this alpha n is the largest coefficient such that the lifting obtained from the original green inequality by adding alpha n xn on the left hand is valid for S. The fact that this alpha n is the largest coefficient that gives you a lifting of the green inequality implies the following property. If the original inequality defines a d-dimensional face of convex intersected xn equal to 0, then the lifting defines a face of convex of dimension at least d plus 1. Now let's prove this proposition. This proposition asks us to prove a number of things. So let's start by showing that the lifted inequality is valid for S. So to prove that it's valid for S, we prove separately that it's valid for all the points in S with xn equal to 0, and then for all the points in S with xn equal to 1. So the simpler one is for the points with xn equal to 0, because we know this by assumption. Let's write it. Great. What about instead the points with xn equal to 1? So the sum for I that goes from 1 to n of alpha I xi less than or equal to beta is valid for the points in S with xn equal to 1 because for every vector x bar in such a set, we have sum of alpha I x bar I for I that goes from 1 to n. So let's break this down into the first n minus 1 components and the very last one. So this is the sum for I equal 1 until n minus 1 of alpha I x bar I plus alpha n times x bar n, which is equal to 1. Now we can upper bound this sum by the max in the definition of alpha n. So this is less than or equal to the max of the sum for I equal 1 until n minus 1 of alpha I xi such that x in S xn equal to 1. And this is exactly because the point x bar is indeed in S and has x bar n equal to 1. And we shouldn't forget plus alpha n. And at this point, this max plus alpha n is exactly beta from the definition of alpha n in the statement of our proposition. Therefore, we have shown that the sum for I equal 1 until n of alpha I xi less than or equal to beta is valid for capital S. Great, so this is the first thing we wanted to show. Now let's prove that alpha n is the largest coefficient with this property. In order to prove this, we show that the vector x star that achieves the maximum satisfies our lifted inequality at equality. Let's write here, let x star in capital S achieving the max, then x star satisfies x star n equal to 1, and we have that the sum for I equal to 1 until n of alpha I xi equal to beta. Why is that? Well, you can go through the chain of inequalities that we just obtained above and see that instead of having less than or equal to, we have equality, and so we have equality throughout, and that's how you obtain this equality. Thus, alpha n is the largest coefficient with such property. Great, so now we've shown this part of the proposition as well. Everything we need to show now is about the dimension of the face. So we're assuming that the original inequality defines a d-dimensional face of convex intersected xn equal to 0, and we want to show that the lifted inequality defines a face of convex of dimension at least d plus 1. So this dimension increases by at least 1. How are we going to show this? Well, we pick d plus 1 are finally independent vectors in the set convex intersected xn equal to 0 satisfied at equality by the original inequality. Clearly, they satisfy at equality also the lifted inequality, and we just need one more point, and this one more point is exactly our x star. So let's write this down. Consider d plus 1 are finally independent points in conv S intersected x with xn equal to 0. Satisfying. Sum for I equal 1 until n minus 1 of alpha I xi equal to beta. These points also satisfy the lifted inequality sum for I equal 1 until n of alpha I xi equal to beta. Then we said we want to consider the vector x star. The vector x star is affinely independent of the previous d plus 1. And this is clear. That's because x star n equal to 1, while all the other points have xn equal to 0. Therefore, sum for I equal 1 until n of alpha I xi less than or equal to beta defines a phase of convex of dimension at least d plus 1. And that's it. We've proven everything the proposition said. Let's get back to the slides. Now that we've understood our lifting proposition, let's look at an example. So let's get back to knapsack sets. Here we have a 5-dimensional knapsack set. We have binary variables, of course, and this one is our knapsack inequality. Now let's pick a minimal cover for this set, and we claim that 1, 2, 3, 4 is indeed a minimal cover, and you can check that. Now the corresponding minimal cover inequality is x1 plus x2 plus x3 plus x4, at most 4 minus 1, therefore 3. We know that minimal cover inequalities are valid for k, so in particular they are also valid for the face of k defined by x5 equal to 0. In order to proceed with our proposition, we need to check the technical condition. So we need to see if k intersected x5 equal to 1 is non-empty. And surely enough it is, because if you set x5 to 1, even if everything else is at 0, that's a point in k. Great, so we can then compute alpha 5 as the proposition tells us. So we pick the right hand of our original minimal cover inequalities minus the max of the left hand of the inequality, such that the feasible region of the problem in the proposition is the original feasible region, but where we set, in this case, x5 to 1. So we have the same inequality until 4x4, but then we have plus 6 less than or equal to 22. Therefore, if we bring the constants to the right hand, we have that the left hand is less than or equal to 22 minus 6. In particular, this is a 4-dimensional integer programming problem, and if you solve it, you obtain that alpha 5 is equal to 1. Therefore, the lifted inequality is the original green one plus alpha 5, which is 1, times x5 less than or equal to 3, which is the original right-hand side. In proposition 7.1, we saw that the green inequality is facet defining for conv k intersected x5 equal to 0. Therefore, the proposition 7.2 implies that the lifted inequality is now facet defining for the full conv k. Note that this inequality looks similar to a cover inequality. For example, one could wonder, is this the cover inequality associated with the cover from 1 to 5? Well, of course it's not, because the right hand of such a cover inequality should be 4. So this inequality is much stronger, because it's less than or equal to 3 instead of less than or equal to 4. Great, so in this example, we've understood how to lift a minimal cover inequality for a 0-1 knapsack set. Now the question is, are you able to lift any minimal cover inequalities for 0-1 knapsack sets? Well, not exactly, at least not directly, because this example was chosen in such a way that you can apply directly proposition 7.2. In fact, the minimal cover inequality contained all the variables until variable n minus 1, and we lifted the last variable. In general, you could have a minimal cover inequalities that contains fewer than n minus 1 variables on the left hand. And the question is, can we then lift also such inequalities? So let's again go to the more general case and answer this question in this more general setting. Consider a general 0-1 linear set, and in this case we need a technical assumption, namely that the matrix A defining the set S is non-negative. We definitely need this assumption, but it's a bit technical at this point, so maybe just forget it for now. I'll get back to it. Now assume that you have a facet defining inequality for convex intersected xj equal to 0, not only for one variable, but for a bunch of variables, all the variables in n minus c. And assume that your inequality is exactly of the form sum of alpha j xj for j only in c less than or equal to beta. And this is exactly what we have in the case of minimal cover inequalities, as we saw essentially in the first slide of this section. Now we can essentially use our lifting proposition to lift this inequality into a facet defining inequality of convex. So what do we need to do? We need to add the sum of alpha j xj for every j in n minus c. The fact is that our proposition 7.2 only allows us to add one alpha j xj at the time. Therefore, what we can do is apply the proposition recursively in order to obtain one by one these coefficients alpha j. So let's just see explicitly what we want to do. So again, we have our inequality that is our starting point, as always in green. It's facet defining for, again, convex intersected xj equal to 0 for every j in n minus c. So what we want to do is pick one by one the indices in n minus c and remove them essentially from here, because we eventually want to obtain an inequality that is facet defining only for convex. And one by one we want to bring them inside the inequality. So let's pick the first index that we want to bring from here to the inequality. So let j1 be in n minus c. Now we apply proposition 7.2, but we have to be a little bit careful to which sets and which variables we apply such a proposition. So clearly the variable that we want to lift is xj1. But then what is the set that we call the capital S inside the proposition? Well, this set changes essentially at every iteration here. In our first iteration, the one we're discussing now, we need to consider the set S intersected xj equal to 0 for every j in n minus c minus j1. In this way, if we apply the proposition, we obtain a lifting of the green inequality where we also have alpha j1 xj1, and it is a facet defining for convex intersected now xj equal to 0 for j in n minus c minus j1. So this is a larger set than the one before, and we're working our way towards having just convex here. In the second step, we take a j2, now it has to be in n minus c, but also minus j1, because now j1 has been lifted already. And now we apply again the proposition 7.2, we want to lift xj2, and the set in the proposition must be S intersected xj equal to 0 for every j in n minus c minus j1, j2. And again, due to the proposition, we are also able now to lift the second variable, and we obtain a facet defining inequality for convex with xj equal to 0 for every j in n minus c minus j1, j2. And so on and so forth. If you continue until you have considered all the indices in n minus c, you will end up with a facet defining inequality for the set convex. So let's see now algorithmically what we have to do in order to perform this sequential lifting. In fact, in this discussion, I didn't even write exactly how to compute the coefficients alpha ji. So in sequential lifting, the first step consists in choosing an ordering of all the indices that we have to lift, those in n minus c. Next, it will be useful to define the sets ch such that at iteration age, ch contains the indices of the variables that appear in the inequality. So at the beginning, or the 0th iteration, we have c0 equal to c, and then one by one we add the j age in exactly the order that we pick them. Now we're only left with the question, how should you calculate alpha j age? And for this, we just need to apply the proposition. We have that alpha j age is beta, this never changes, is the original right hand, minus the max of the sum of alpha j xj for j in c age minus 1, and this is the left hand side of the lifted inequality obtained so far, such that x is in S and xj is 0 for every j in n minus ch, and xj age equal to 1. At this point, if you remember, a couple of slides ago, we made a technical assumption that our set S has dimension n and defined by a matrix that is non-negative. And the question is, why did we need those technical assumptions? And the answer is we need these assumptions in order to apply proposition 7.2. In fact, if you remember, in order to apply such a proposition, we need to check a couple of conditions, and it's a very good exercise to check that in fact the hypotheses of the proposition are satisfied at each iteration. And that's exactly where you need to use our assumptions that the dimension of S is n and that A is greater than or equal to 0. In particular, you need this A greater than or equal to 0 to show that for every point in S, then also all the points that are binary and with x upper bounded by x bar are contained in S as well. Once you've checked that the hypotheses of proposition 7.2 are always satisfied, then indeed proposition 7.2 implies that the full inequality that you obtain at the very end, so the one with all the coefficients alpha j for j equal to 1 until n, at the very end is facet defining for the convex hull of S. Let's see an example of sequential lifting. As always, we look at a 0-1 knapsack set. Here it is. This example is very similar to the previous one, we just have more variables essentially. Now, in fact, it is a 7-dimensional problem. As before, 1, 2, 3, 4 is a minimal cover, and the corresponding minimal cover inequality is this one in green, x1 plus x2 plus x3 plus x4 less than or equal to 3. And now we perform sequential lifting according to the order, let's say 5, 6, 7. Therefore, first we want to understand the coefficient alpha 5. And it's defined as right hand side, so 3 minus max of left hand side of the inequality, subject to, so what we need to do is pick the original inequality, set x6 and x7 to 0 and x5 to 1. And this is the inequality that we obtained. This is a 4-dimensional problem, and if you solve it, you obtain alpha 5 equal to 1. Next, we want to find alpha 6. At this point, we're considering the inequality that we just lifted. So the right-hand side is always the same, it's 3. But then in the max, we have the new left-hand side. So we also have plus alpha 5 x5. And the constraint is the original constraint where we set x7 to 0 and x6 to 1. This is a 5-dimensional problem, and we obtain alpha 6 equal to 0 if we solve it. Finally, what about alpha 7? Again, 3 minus the max of the current lifting. Now we have plus x5 as before, plus alpha 6 x6, which is 0 because we obtained alpha 6 equal to 0. Now the inequality is the original one where we set x7 to 1 and we obtain this inequality. This problem has dimension 6, and if you solve it, you obtain alpha 7 equal to 0. Therefore, the final lifted inequality is the following: x1 plus x2 plus x3 plus x4 plus x5 less than or equal to 3. Note that our problem was extremely symmetric because in the knapsack inequality we had the same weight for x5, x6 and x7, and so by symmetry you can check that if you picked any other order of the variables for the sequential lifting, we would have obtained the following inequalities. It's always the first that gets a +1 coefficient, and the second and third we get a 0 coefficient. So you obtain the same inequality as the one we have seen in detail, but with plus x6 and plus x7 instead of plus x5. We know by proposition 7.1 that the original inequality is facet defining for the corresponding phase, and by proposition 7.2 the inequality obtained at the end of our sequential lifting is facet defining for the full set. So all these inequalities are facet defining for conv k. In particular, in this example, we've understood that if you pick different orderings of the variables to be lifted, you may obtain different lifted inequalities. Now, an interesting question that you could ask at this point is, can you obtain any possible lifted inequality with the sequential lifting? And the answer is unfortunately no. So this is just an example to convince you of this fact. Look at this inequality. It's x1 plus x2 plus x3 plus x4 plus 1 half x5 plus 1 half x6 plus 1 half x7 less than or equal to 3. By definition, this is again a lifting of our original minimal cover inequality. And you can check that it is not only valid for the knapsack set, but it's also facet defining. However, this inequality cannot be obtained by sequential lifting. Well, there are several ways to see that. You can either try every possible sequence, which essentially we've done, but there's also one very quick way to note that. In fact, by construction of sequential lifting, all the coefficients that you obtain in the lifting process are integer, so you will never be able to obtain fractional coefficients. So this is an example that shows that not all lifted inequalities, not even among the facet defining ones, can be obtained sequentially. And this concludes our video on lifting.